Welcome back, students. In this video, we're going to look at alkyne acidity. A while ago, we considered alkyne acidity, but now we're going to look at it in the context of reactions. When we consider alkynes, just remember that alkynes are really not very acidic. If we're looking at pKa's, a terminal alkyne, where a terminal alkyne means at the end of a molecule, so there's actually a hydrogen to pull off, because if it was an internal alkyne, that would mean there's carbon on either side and there's no hydrogen to pull off. So we're looking at terminal alkynes where there's a hydrogen, like I just highlighted in yellow. This has a pKa of 25. Remember from long ago that the lower the pKa, the stronger the acid. Well, the acids that you're used to, like HCl, have pKa in like the -7 range. So this is not something that you would really call acidic in the world of, acids and bases when you're comparing to things that are actually acidic. That being said, acidity is all relative. So in comparison to the other carbon-hydrogen bonds, the alkyne is actually pretty acidic. Because if you look at an alkane, that pKa is 50. That's going to be very, very, very difficult to pull off. The hydrogen on an sp2 hybridized carbon, pKa of 44. So in the world of relative pKa's, alkynes are your most acidic of these carbon-hydrogen bonds that I'm showing here. The basis of some of our future reactions is forming something called an alkynide ion. So let's talk about how that's going to happen. When you have a terminal alkyne, the fact that this proton is one that is more easy to pull off than the other protons we discussed on the earlier page makes us have the ability to use a strong enough base that this kind of reaction can happen, where we can have a proton transfer and get this negatively charged carbon. Right? Negatively charged carbons are called carbanions. And this one has a special name because the lone pair is on a carbon that's sp hybridized. It's called an alkynide ion. And I'm just going to pull that pi bond a little further. That looks good. So what bases are strong enough? Which ones are going to make the cut? So this one, amide, NH2-, which sometimes you'll see as sodium amide, where that sodium, it's just a spectator ion. It's not doing anything for your reaction except getting the amide into solution. So if you see NaNH2, that's the same as someone just writing NH2-, and I like to include my lone pairs. Another strong base is going to be sodium hydride, so NaH, which is the same thing as if you see H- with a lone pair. There's another one called butyl lithium, and butyl lithium looks like this. People will draw it out a variety of ways, but this is the structure. It's a butyl with a lone pair, and then the lithium's the counter ion. There's one other base that you can commonly see. It's called LDA. So people will just abbreviate it as LDA. It's called lithium diisopropyl amide. And let's just draw that out really quick. So it's got two isopropyl groups, but it's an amide, so it's a negative nitrogen. And then there's a lithium as its counter ion. So the lithium's just hanging out close by, having a positive charge. Notice how LDA has a negative nitrogen, and so does the amide ion. So these are things that are able to pull off that proton. Things that can't pull off the proton, hydroxide. Any O- is not strong enough. Right? And you can go back to your pKa stuff and your weak acid and weak base and strong acid, strong base stuff from way back in the beginning of the chapter and utilize that information to see why. Here's the cool part about the alkynide ion. Once the alkynide ion is formed, we use it in subsequent reactions. We use it to lengthen the carbon chain. And that's actually really special because out of all the reactions you've learned so far, not many of them add carbon. You've seen cleavage and oxidative cleavage. You've seen adding, functional groups like bromines. You've seen adding OHs. You've seen turning OHs into ketones, things like this. But you have not really seen the addition of carbon because there's not a lot of reactions that add carbon, but this is one of them. Once you have the alkynide ion, what can happen is an SN2 reaction. So you go ahead, you add an alkyl halide with a good leaving group that is unhindered, and you end up getting an SN2 reaction. And this lengthens the chain. You just need to make sure that you're counting your carbons. So what I mean by that is I had 1, 2, 3 carbons to start with, and 1, 2, 3 carbons here. And I just added 1, 2 carbons, so I added 1, 2 carbons. Now, one of the things you might have realized so far is that I've purposefully drawn my alkynes 2 different ways. The ways that I've drawn my alkynes are one way where I draw the long line and then the 2 pi bonds, one on top, one on bottom, so that there's no space right here where I'm highlighting in yellow. Where that triple bond ends, there's a carbon there. All right, so this is 1, 2, 3 carbons. Another way to draw your alkyne is to draw that line and then separate the triple bond. And that's also showing 1, 2, 3 carbons. This one, I don't know, I'm going to redraw this one. I don't love it. I'm just going to make that, different color, one long line. I want you to be prepared for both ways. That little space, sometimes if you get into a routine where your instructor shows you one way and then you see the little space or the little space disappears, you freak out, right? So I just want you to know that both ways are acceptable ways to draw your alkynes on paper, and that where the triple bond ends, there is a carbon. Now, if we take this idea of adding alkyl groups using our alkynide ion, and we kind of back up and use our earlier idea about forming the alkynide ion, this is how the reaction is going to look. You're going to start with a terminal alkyne. You're going to see that we add sodium amide. Don't be surprised if someone puts like comma NH3 for that, because that is the solvent. And then you add your alkyl halide. Don't be surprised if, because this is an SN2 reaction, that someone throws a polar aprotic solvent in for step 2. Overall, you'll draw the product, which is this. And I'm just going to go back and double count my carbons, right? 1, 2, 3, 1, 2, 3, and then 1, 2, 1, 2. I always encourage you to double count your carbons, especially when you're adding carbon, so that you don't miss anything. Our eyeballs can play tricks on us. Let's wrap up. In this video, we talked about the acidity of terminal alkynes. Here, I'm saying it has an acidic proton because if we were to compare to things that you actually learned were acids in general chemistry, that it would not be considered very acidic at all. But in this context, we have a strong enough base to pull off that proton. Once we pull off that proton, we make the alkynide ion, and then we can utilize the alkynide ion in an SN2 reaction to lengthen the carbon chain, which is called an alkylation reaction. Thanks so much for watching. This is Katoni signing out.